Settle in with a warm drink and a soft light. We'll wander toward the deepest shadows in the universe and find steady ground there. No rush, just clear steps. Black holes sound like endings, yet they're part of how galaxies live and change. They press on our ideas about space, time and matter, turning hard questions into simple shapes we can picture. With a few plain images, we can see why the darkest places can teach us how everything holds together. You hold a mug by a window and feel its warmth against your palm. Outside, the night is a deep field. A few stars blink like distant porch lights. That mix of closeness and far away is where black holes begin to matter. They aren't just exotic stamps in an atlas. They sit in the hearts of galaxies and tug on the long story of who we are and where our atoms came from. Think of a city map at night dotted with hubs where roads meet. Galaxies have hubs too, and many carry giants at their centres. These giants are black holes with millions or billions of times the sun's mass. They don't sit idle. As gas falls in, it heats and shines, and that light and wind can shape how new stars are born. Sometimes the hub is quiet, sometimes it flares. In both moods, it governs the city around it. In smaller neighbourhoods, the size of a few suns, there are black holes made from dead stars, hidden in pairs with normal stars sipping matter and glowing in X-rays. They're common enough that statistically one may drift within a few thousand light years of us. Not close, but not storybook distance either. They also matter because they nail down the edges of our best ideas. Gravity in most places is gentle, the curve of a bull's path, the chill at dawn. Near a black hole, it shows its full character. Space and time are not a stage, but a fabric that can fold and stretch. In Einstein's general relativity, mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Black holes are where that dance goes to its limit, with a boundary called an event horizon, a surface beyond which paths only go inward. We learn a lot by tracing the steps right up to that line. They press us on time itself. A clock near a black hole, one that ticks evenly in its own shape, will seem to slow to a faraway observer. Signals are delayed, colours redden, and the idea of now becomes local. It's not a trick, it's how the world is built when gravity is strong. And in that strength, questions arise. What happens to the details of what falls in? How do quantum rules, which work cleanly for atoms, meet the vast curve of gravity near a horizon? These are the quiet arguments of modern physics, and black holes sit at their centre. Some proposals for how information escapes rely on subtle correlations in outgoing light or exotic structures near the horizon that have not been observed. If this all sounds remote, here's the link to your mug and window. The iron in your blood was made in stars that lived and died under gravity's orders. Black holes end some of those lives and regulate others. The Milky Way's centre, with its own giant, may have paced the growth of our galaxy's arms, which shaped the cloud that formed the Sun and Earth. When astronomers tuned the Event Horizon Telescope and the LIGO detectors, the tools they built flowed into cameras, computing and materials that touch daily life. The path to a black hole runs through your phone's sensors, your GPS, your MRI, your weather forecast. The dark is not a part, it's stitched into what is near. But before we begin, let me ask you something. I'd love to know, where in the world are you listening from tonight? And what time is it for you, under your sky? Share it in the comments below. I think it's wonderful that we can be here together, scattered across the planet, yet united in this journey through the life of the stars. The journey begins in silence. There's another reason these objects matter. They take fear and turn it into clarity. The phrase "nothing can escape" sounds like doom, yet the region outside the horizon is rich with energy and order. Matter there forms rings, jets and waves we can map and understand. With patience we can even make images of the shadow a black hole casts against glowing gas. That is not science fiction, we have seen it. The dark core becomes a tool, a clean edge to draw against, and there's a softer gift. Thinking about black holes makes us careful with words like forever and nothing. It shows that limits, when understood, can be generous. A horizon is a boundary, yes, but it is also a promise, a place where our best tested physics holds and gives crisp answers. The unknown may lie deeper in, yet the approach is solid ground. For a late hour in a quiet room, that is enough to begin. You tip a glass baking dish and watch a shallow pool of water lean to one side. Coins at the bottom slide as the surface tilts, guided by the shape of the dish more than by any hand. That's the image to keep as we talk about gravity. Not a string pulling down, but a shape that things follow. In everyday life, we say gravity pulls, as if it had fingers. The older picture, from Newton, works well here. Forces act at a distance and draw masses together. But the deeper view is softer. In Einstein's general relativity, gravity is geometry. Space and time form a four-dimensional fabric called spacetime. Mass and energy curve this fabric, like that tilted dish, and objects move along the simplest possible paths within it. Those paths are called geodesics, the straightest possible lines in a curved place. You don't feel a force when you're gliding along one, you feel forces when you're pushed off it. Imagine a bus rolling over a gentle hill. Passengers standing feel heavy or light as the floor presses on their feet. They blame gravity, yet the hill's shape is what changed their weight. In the same way, planets orbit because space-time near the Sun is curved. They're not being yanked, they are following the cleanest lines allowed by the shape. Light, which has no mass, also bends near stars. It follows geodesics too, and the fact that its path arcs tells us space-time is curved, not that light has gained weight. We test this picture with care. Clocks run at different rates at different heights, as measured by GPS satellites and ground stations. Starlight shifts as it skims past the Sun, seen during eclipses and now with radio precision. The orbit of Mercury precesses in just the way the geometry predicts. These quiet agreements add up. In strong fields, the curve deepens and new shapes appear. Event horizons and trapped surfaces, places where every path leads inward. The equations that describe this are complex, but the idea remains simple. You pour water into a deeper bowl, and the surface leans more. There is a neat consequence of geometry. If an astronaut coasts in a spaceship far from any mass, they feel weightless because they follow a geodesic. If an elevator cable snaps, a person inside feels weightless on the way down, not because gravity is switched off, but because they are in free fall, moving with the curve rather than pushing against it. Weight in this view is the name for the support force that keeps you from following your natural path through space-time. In a chair, the seat holds you up and you feel heavy. Let go, and you fall along the shape. Curvature itself can be measured. Think of drawing a triangle on a flat table. Its angles add to 180 degrees. Draw a triangle on a curved ball, the angles add to more. Space-time does something similar. The presence of mass changes the sums of angles and the lengths of paths in a way that can be mapped by how test particles and light beams move. That is what we mean by saying mass tells space-time how to curve. The geometry contains the force. Black holes are the deepest bowls we know. The curvature is so strong that inside a certain boundary, no path leads out. Yet even here the language of shape helps. Outside the horizon, you can orbit, hover with rockets, or skim past depending on your energy and aim. Inside, all time-like paths, the routes for anything with mass, lead to the centre. The fabric's shape decides. At the smallest scales, quantum effects may roughen this fabric, replacing smooth geometry with something foamy or discrete. We don't have the final theory that unites quantum physics and gravity, so we treat space-time as smooth, where experiments say it is, and stay gently honest about the rest. The good news is that the geometric picture isn't only elegant, it's practical. It guides the timing in your phone and the orbits of satellites. It lets astronomers weigh black holes by watching stars curve around them. It predicts the ripples in space-time that we now measure as gravitational waves, and for each of these the everyday image holds a shape we can map, a path we can follow, a world that bends and shows us how to move within it. You've watched a campfire burn low, bright tongues shrinking to red coals, then ash. A star does something similar, though the times are far longer and the fuel is stranger. It starts hot and lively, then settles, then quietens, and sometimes ends with a collapse that leaves a dense remnant behind. At first, a star is a puffed ball of gas held up by its own heat. Deep inside, hydrogen fuses into helium. That fusion releases energy, which presses outward and balances the inward pull of gravity. This balance has a name: hydrostatic equilibrium, a simple truce between push and pull. As hydrogen runs low in the core, the star adjusts. It swells into a red giant, or if it's massive, it goes through more stages, fusing helium into carbon and oxygen, then into heavier elements, like stepping down through embers toward ash. The key is that fusion makes lighter elements into heavier ones until it reaches iron group nuclei. Fusing iron doesn't pay back energy, it costs it. So when a star's core becomes iron-rich, the furnace falters. Without enough outward pressure, the core can't resist gravity's squeeze. For stars like our Sun, the story ends earlier. They never get hot enough to make iron. They blow off their outer layers in a gentle planetary nebula and leave behind a white dwarf, a dense ember about Earth-sized, held up by electron degeneracy pressure. That phrase means that the electrons, by the rules of quantum mechanics, resist being packed too tightly. Their resistance props up the star's corpse. There's a limit to that support called the Chandrasekhar limit, about 1.4 times the Sun's mass. Pile more mass on a white dwarf and the electron's pressure can't hold. Carbon ignites explosively in some cases, making a type I a supernova. Or, if the core is heavier from the start, gravity presses harder. Electrons are squeezed into protons, making neutrons and neutrinos, and the core collapses. The sudden stop of that collapse can bounce the outer layers outwards in a core collapse supernova, leaving behind a neutron star, a city-sized sphere held up by neutron degeneracy pressure and nuclear forces. Again, there's a limit. Above about 2 to 3 solar masses in the core, the exact number depends on details of nuclear physics. Even neutrons can't hold the line. The remnant collapses further. There's no known pressure that balances gravity at that point. A black hole forms, a region with an event horizon, a surface that marks no return. The road to that horizon starts in ordinary starlight, fusion, balance, cooling, and passes through thresholds set by quantum rules and the stiffness of nuclear matter. Not all paths to remnants are alike. Some massive stars may collapse straight to black holes with little visible light. Others explode and then fall back, feeding the new black hole with returning debris. In pairs, stars can strip each other's envelopes, changing the masses of the cores and the kind of remnant left. Metallicity, the fraction of elements heavier than helium, also matters. Low metallicity stars lose less mass to winds, keeping their cores heavy and making black hole birth more likely. In the early universe, the very first stars may have grown huge and short-lived. Some of those first giants might have seeded early black holes that later merged and fed to become the monsters we see in galactic centres. We read these endings in the sky. Supernova remnants glow in filaments, shock waves lit by their slam through space. Neutron stars blink as pulsars, their magnetic beams sweeping past us like lighthouse lights. Black holes in X-ray binaries flare and fade as they sip from a companion star, the pace set by how gas spirals in. The simple image of a fire dying to embers is not far wrong. The universe makes coals, and some are so dense that light itself cannot climb away. The satisfying turn is that death feeds life. Supernovae seed space with carbon, oxygen, calcium, iron, the stuff of rocks and blood and bread. Remnants stir the gas and sculpt the next round of stars. The road to collapse is also a loop, a way of making new lights from old. So when we speak of black holes, we're not speaking of voids that steal from the universe. We're speaking of the steady housekeeping that keeps the long night interesting and rich. You stand beneath an old bridge and feel the weight of stone in your chest. Look up at the arch. Elegant, sure, each block leaning on the next. It holds, until something gives and the span drops. That sudden surrender is a guide to how a massive star gives way and a black hole is born. Inside a heavy star, the core is an engine room stuffed with iron at the end of its life. The outer layers still burn in shells, but the centre is tired. Once iron dominates, the core can't release more energy by fusion. Gravity presses in. Electrons and protons merge into neutrons, making an avalanche of neutrinos that race out. The core collapses in milliseconds, shrinking to a sphere only tens of kilometers across. The infalling outer layers smash into this new wall and may bounce, sending a shockwave outward. If that shock is re-energized through neutrino heating, turbulence and nuclear matter effects, it blows the star's envelope apart. The aftermath is a neutron star. If the core is heavier, the collapse doesn't halt. The event horizon forms and sweeps outward, swallowing the failing star from the inside out. The thresholds are set by mass and structure. The iron core needs to be roughly 1.5 to 2.5 solar masses for the collapse to make a neutron star. Above that, even the stiffness of neutron matter can't fight gravity. The exact tipping point depends on the equation of state, the relationship between pressure, density, and temperature deep in nuclear matter. We don't know that relation perfectly, but observations of heavy neutron stars near 2 solar masses suggest a stiff enough core up to that point. Past it, the bridge falls. Some stars skip the bright crash. Direct collapse can occur when the star is so massive or so stripped of support that no strong shock forms. The outer layers fall in quietly. A black hole appears with only a faint whisper of light, maybe a slight dimming as the star vanishes. Others collapse, explode weakly, and then much of the ejected material falls back. This fallback can tip a newborn neutron star over the limit, finishing the job and leaving a black hole a few seconds later. Binary partners change the script too. Mass transfer can bulk up one star's core or peel away its outer layers, altering the moment when the arch gives way. Meanwhile, neutrinos carry most of the gravitational energy away. In the brightest explosions, they flood outward, barely interacting, yet their sheer numbers heat material behind the shock and help it push through. Rotation and magnetic fields complicate the picture further. A spinning core can flatten, launch jets, and stir the collapse. In some cases, a rapidly spinning, strongly magnetized core, a magnetar, may form briefly and drive energetic outflows before collapsing to a black hole. Astronomers watch for the signatures. Supernova light curves tell us about the energy dumped into the ejected layers. Spectra reveal what elements were cooked. Neutrino detectors have already caught a handful of particles from a nearby supernova, a tantalizing whisper. Gravitational waves may soon trace the wobble and roar of a collapsing core, adding texture to the story. Piece by piece, the method of failure comes into view, like spotting which stone in the arch shifted first. The practical lesson is simple and quiet. Nature uses thresholds. When support is enough, balance holds. When it isn't, collapse is not a moral fall, it's a clean transition to a new state. A black hole is not born from malice. It arrives when the available forms of pressure can no longer hold up the weight. The bridge releases, and in that release a new kind of structure appears, one described not by the pressure of particles, but by the geometry of space-time itself. Stand beside a river and watch leaves drift. Upstream they meander, caught in eddies, then suddenly the water quickens toward a low falls. Near the lip, every twig seems fated to go over. That line is our way into the idea of an event horizon, the place from which no path bends back. Far from a black hole, space-time is only gently curved. Light and matter can go almost as they please. As you move closer, the current strengthens. The event horizon is the boundary where even light, which is as fast as anything can be, cannot make headway against the inward flow of space-time. It's not a wall in space, it's a point of no return in the geometry. Cross it, and all future paths lead inwards. The term is plain. Events inside can't affect what happens outside since no signal can climb out. From the bank you can hover with rockets, holding position even near the brink. You'll need more and more thrust as you get closer. Sit just above the horizon and your fuel burns at a terrifying rate. Drop something in and watch how it appears to slow and dim, never quite crossing in your view. That's because the light from the falling object is stretched by gravity, gravitational redshift, and its arrival is ever more delayed. To the falling object, though, the crossing is ordinary. No bang, no flare, just a smooth passage into a region where all roads lead downriver. The horizon has a size set by mass. For a non-spinning, uncharged black hole, the radius is roughly 3 kilometers for each solar mass. Bigger holes have bigger, more leisurely horizons. Supermassive ones at galactic centers have lips so gentle that a person crossing would feel little tide at that moment. Small ones made from stars have horizons where tides are brutal and quick to notice. Spin changes the story by dragging space-time around with it, shrinking the horizon a bit and adding an extra region outside called the ergosphere, where everything is forced to co-rotate. Importantly, the horizon is not where suction becomes strong. The pull you feel outside depends on distance and mass, and it's no worse near a black hole than near any object of the same mass and size. What's different is the inside. A star has a surface you can hit and stand on, at least in principle. A black hole has none. There's no place to stop and rest once you pass the horizon. Geometry alone directs you to the centre. We measure horizons indirectly. The first direct images of black hole shadows, the dark bowls against glowing gas, show us the silhouette of the photon sphere, a region a bit outside the horizon where light can orbit. From that outline, we infer the horizon's size. We also weigh black holes by watching stars and gas move around them, and by timing the vibrations of space-time when black holes merge, imprinted in gravitational waves. All these methods point to the same humbling shape, a smooth boundary defined by the flow of space-time, not by any substance. Some theories suggest subtle structures may sit at or just outside the horizon, perhaps due to quantum effects. No evidence requires them, and the classical picture of a clean horizon works beautifully for all observed phenomena so far. The quiet reveal is this: the horizon is a kindness to our thinking. It gives a clear edge to an otherwise messy problem. Outside, physics is crisp, testable, and rich. Inside, we acknowledge our limits and carry on mapping the bank, the eddies, and the leaves that still lie within reach. You trace a finger along a spinning record and feel the groove guide you. The closer to the centre, the tighter the turns, the more the needle must commit to the path. Near a black hole, space-time has its own grooves, and the paths of light and matter ride them with few options to stray. In flat space, the straightest path between 2 points is a straight line. In curved space-time, geodesics take their place, and near a black hole those geodesics bend in strict, beautiful patterns. Picture a grid of lines, each telling a particle or a light ray where to go if nothing pushes aside. Far out, the lines are almost straight. Closer in, circles tighten, plunges steepen, and there's a special ring where light can orbit in perfect circles, precariously balanced. This is the photon sphere. A slight nudge sends a photon either inward or outward, like a coin on a dinner plate's rim. For matter, the story is about choices getting narrower. A rock tossed toward the black hole from far away can still miss if it's aimed right. Closer in, it must thread a needle to avoid capture. If it has some sideways motion, it may settle into an orbit for a while. But even these orbits change character as you approach. There's a final ring of stable circular paths for material with mass, the innermost stable circular orbit, or ISCO. Inside that, no amount of careful steering keeps you circling. The groove carries you inward. Spin complicates the grooves. A rotating black hole drags space-time around it. A soft, relentless twist called frame dragging. Paths co-rotating with the spin can come closer instably than those going against it. The photon sphere and the ISCO shift accordingly. There's also the ergosphere, a region where the twist is so strong that nothing can stay at rest relative to distant stars. Everything is swept along and must rotate, yet even here a clever dancer can do a trick. Tap the spin's energy through interactions and emerge with more than they had. That's the Penrose process in outline, an elegant exchange made possible by the geometry. Light shows the grooves clearly. Rays passing near the black hole bend around it, sometimes looping many times before escaping. To a distant eye, this makes rings and arcs, gravitational lensing. stacked echoes of light that skimmed by at different depths. Matter traces the grooves too. Gas pulled from a star can form a disk, its inner edge near the ISCO. Heating and friction in that disk make it shine, the colour set by how deep the grooves go before a plunge begins. Observing those colours and hotspots lets astronomers sketch the layout, like reading a record by ear. A person falling inward follows a time-like geodesic. Their path is as calm as any freefall, until tidal forces grow strong enough to stretch and squeeze. From the outside, their image slows and fades. From their perspective, the centre arrives on schedule. The near-horizon space-time is smooth in the classical picture, and the paths through it tell a simple tale. Geometry dictates motion, and the options narrow gracefully. If quantum effects roughen the horizon, the grooves may carry subtle noise. Some proposals predict near-horizon echoes in gravitational wave signals from black hole mergers. Current data are consistent with the smooth case, but the search is ongoing. What's lovely here is the sense of order. Near a black hole, chaos gives way to clear lines. Freefall is honest. Orbits have names and limits. Light draws rings. And all of it comes from a single idea. The world has a shape, and things move as that shape allows. Place a finger on the groove and listen. You watch cream pour into coffee and bloom into spirals, thin threads curling and brightening the cup. A black hole, for all its darkness, can make light in a similar way. Matter that gathers and swirls around it heats and shines, and sometimes it spits out jets that lance across space. Start with the disk. When gas falls toward a black hole, it rarely plunges straight in. It carries sideways motion, angular momentum that keeps it from a direct drop. Like cars merging onto a roundabout, the gas settles into an accretion disk, a thin, rotating ring where neighbouring layers rub. That rubbing is viscosity, a measure of how layers drag on each other. In space, the microscopic stickiness isn't enough. Magnetic fields step in, tangling and amplifying through a process called the magnetorotational instability. This turbulence moves angular momentum outward and gas inward. The inward gas loses gravitational energy, and that loss shows up as heat and light. The inner parts of the disk can get incredibly hot. Around stellar mass black holes, the inner disk glows in X-rays. Around supermassive black holes, it shines in ultraviolet and visible light. The efficiency is remarkable. Up to about 10% of the mass energy of the falling gas can be radiated away, much more than ordinary chemical burning. The disk's inner edge sits near the ISCO. Inside that ring, the gas's orbit is unstable, so it plunges in quickly, giving up its last energy as it falls. Jets are the surprising counterpart. Perpendicular to the disk, narrow beams of particles and fields shoot out at near-light speeds, reaching far beyond the galaxy. They can light up radio lobes tens or hundreds of thousands of light-years across, painting the sky with long, ghostly fingers. The power behind jets likely comes from the black hole's spin and the disk's magnetic fields. Twisted field lines anchored in the disk and threading the horizon act like wires, extracting rotational energy and channeling it outward. This is the Blandford's-Narjek mechanism in plain terms. Use magnetic tension to tap the hole's spin. The details of how fields organise and hold together over such distances remain under study, with simulations and observations closing in. We read disks and jets through their flickers and colours. Hotspots in the inner disk orbit and modulate the light, a kind of lighthouse pattern that tells us about the spin and the inner edge. X-ray spectra show reflection features. Iron lines smeared and skewed by Doppler shifts and gravitational redshift. Radio maps trace the jets knot by knot as they wiggle and brighten. When the feeding rate changes, so does the whole look. Disks thin or puff up, jets flicker on and off, like the coffee blooming differently with a faster or slower pour. This light is not just for show. In active galaxies, the energy from disks and jets feeds back into the galaxy's gas, warming and stirring it, and sometimes shutting down star formation in the bulge. In clusters of galaxies, jets inflate bubbles in the hot plasma. keeping the cluster from cooling into a catastrophic rain of new stars. The black hole, dark at its core, becomes a thermostat for its city, holding the temperature where the system can breathe rather than burn. From an everyday vantage, that's the gentle twist. Darkness, handled in this way, is a power plant. It takes falling matter and turns it into light and wind and radio beams. The process is not perfect, and not every black hole has a strong disk or jets at every moment. Yet across the sky, from small to giant, the pattern repeats: swirl, heat, shine, and sometimes shoot. The cup glows and the threads of cream trace the currents we've learned to read. You spin a coin on a tabletop and see how it hums, wobbling faster as it tightens. Turn it with a bit more flick and it sings a different tone. Black holes have their own spins and, in theory, charges too. These traits change the space around them, giving each a kind of personality. Spin comes first. Most black holes are born with rotation because their parent stars turned. In general relativity, a spinning black hole is described by the Kerr solution. The spin drags space-time around with it, frame dragging, so that objects nearby are swept along. This leads to the ergosphere, a region outside the horizon where nothing can stand still relative to faraway space. The horizon itself shrinks as spin increases, and the ISCO moves inward for co-rotating orbits, letting disks shine more efficiently. In the extreme, a maximally spinning hole allows orbits almost twice as efficient as a non-spinning one. Charge is the other parameter in principle. The Reissner-Nordström solution describes a charged, non-spinning black hole. In practice, astrophysical black holes are neutral. Any net charge would quickly attract the opposite charges from surrounding plasma and neutralize. So charge matters more as a teaching tool than as a feature of the holes we see. Still, mentioning it shows how spare the theory is. In classical gravity, a black hole is fully described by mass, spin, and charge. This is the no-hair idea, bald objects with few traits. Real systems break the baldness with disks and fields outside, but the hole itself keeps its simple wardrobe. Spin can be measured. In X-ray binaries, the inner edge of the disk imprints itself on the spectrum. Faster spin brings the edge closer in, boosting high-energy light. Ion emission lines reflect and smear. The pattern reveals how close the gas can orbit. In gravitational wave data from merging black holes, the spin leaves fingerprints on the chirp's shape, twisting the signal as the pair spirals and coalesces. Piece by piece, we find that many black holes do spin, some quite fast. Others are modest, perhaps slowed by past accretion that arrived in misaligned bursts, cancelling rotation. Spin also feeds the powerhouse. Jets likely draw their energy from it. The faster the spin and the stronger the magnetic fields, the more easily the system can launch and sustain long beams. Observations show a loose link between spin estimates and jet power, though the environment and feeding rate add noise. The exact conditions that switch jets on or off remain unsettled, with different accretion states and magnetic flux levels competing in simulations. On a human scale, the metaphor is homely. Some tops twirl low and steady, some skate and precess. So too with black holes. Their spins simplify the math and complicate the sky. Around a fast spinner, the disk runs hotter, the photon sphere is closer, and time's dilation is stronger. Navigation changes. Falling in feels the same at the horizon. There's no special ring of fire in classical theory, but outside, paths are more twisted. A compass aligned to distant stars will turn in your hand without any motor, a quiet demonstration that space itself is in motion here. The gentle reveal is that personality in this case is not a flourish. It is the structure of the stage. A hole's mass sets the scale. Its spin sets the rhythm. Charge, if it ever shows itself in nature, would tweak the pattern. And while the core remains simple in its description, the surroundings bloom with variety, giving astronomers many ways to listen and learn. You walk a running track and feel the lanes curve beneath your feet. On the straight you can cruise. In the bend you lean and commit. Near a black hole, orbits have their own track, and there's a last safe lane where steady circling ends. Inside it, even the sure-footed plunge. Orbits around any mass can be stable or unstable. In Newton's world, you can circle a point mass at any radius if you go at the right speed. In the curved space-time of a black hole, the menu is shorter. For material with mass, there's a minimum radius where circular orbits are stable, the innermost stable circular orbit, the ISCO. Outside it, disks can form and last. Inside, small nudges grow, and the path spills inward. For a non-spinning black hole, the ISCO sits at 3 times the horizon's radius. If the hole spins and you orbit with the spin, the ISCO moves closer in. If you go against the spin, it moves out. The photon sphere is a separate feature. It's the lane where light itself can orbit in a perfect circle. It lies outside the horizon and outside the ISCO. Unlike massive particles, light on this ring is on a knife edge. A tiny push sends it away or down. The existence of the photon sphere explains the shadow images we make, the bright ring around a dark centre. Light that skirts this sphere can loop around the hole and reach us, stacking up into a narrow bright band. We see the ISCO's mark in the colour and timing of accretion disks. As gas spirals in, its temperature climbs. The inner edge sets the highest energies we see. If the ISCO is closer, the disk is hotter and more efficient, and the spectrum shifts. X-ray observations of black hole binaries use this to estimate spin. Variations, flickers and quasi-periodic oscillations add more clues. Hotspots orbiting near the ISCO imprint their lap times on the light, letting us measure how the track curves. For planets and stars circling a black hole from a comfortable distance, Newton's rules still work well. The trouble starts only when you play near the inside lanes. There, precession becomes strong. An object on an ellipse will see its closest approach point drift around the hole each orbit, a dramatic version of Mercury's gentle precession around the Sun. If the orbit dips too low, it will intersect the ISCO and the path will decay. Energy and angular momentum leak into the disk or into gravitational waves depending on the partner, and the object falls inward. In extreme mass ratio in spirals, small compact objects spiralling into supermassive black holes, the ISCO is the last quiet moment before a plunge. The waves from these systems will carry precise maps of the space-time, letting future observatories like LISA read the metric like Braille. If there are departures from the Kerr geometry, subtle bumps in these inspirals could betray them, offering tests of gravity in its strongest regime. The tidy end to this picture is reassuring. There is a limit, and it is clean. For disks, it's a natural inner edge. For orbits, it's a boundary between can last and must go. In a universe full of messy transitions, the ISCO stands out as a clear lane marker, painted by geometry itself. You pull a piece of soft taffy and watch it stretch into a thin, glossy thread between your fingers. It narrows, trembles, and finally snaps. Gravity can do something similar to matter near a black hole, drawing one end with more strength than the other, turning solid things into long strands. Tidal forces are the difference in gravity from one place to another. On Earth, they lift the oceans by a metre or two and tug very gently on your body. Near a compact mass, the differences grow fast. If you fall feet first toward a black hole, the pull at your feet can be stronger than at your head. The result is stretching along the line to the hole and squeezing sideways. In stories, this becomes spaghettification, a cartoon name for a real effect, the rise of tides strong enough to rearrange anything, from clouds of gas to stones to bone. Whether you notice tides at the horizon depends on the black hole's mass. For a supermassive black hole, the horizon is large, and the gradient in gravity there can be mild. You could cross with no immediate drama, only feeling the tides become dangerous deeper in. For a stellar mass black hole, the horizon is small and the gradient is severe. Tidal forces can rip you apart well before you reach the horizon. The same principle applies to stars. A star that wanders too close to a massive black hole in a galactic centre can be torn into a stream, a tidal disruption event. Half the debris escapes, half falls back and lights up as it accretes, a bright flare that fades over months to years. Tides also work within disks. Clumps of gas are stretched into arcs. Orbits precess. Resonances extract energy and angular momentum. In pairs of compact objects, two neutron stars or a neutron star with a black hole, tidal effects leave marks on the gravitational wave signal. The timing and shape of the wave tell us how stiff neutron star matter is, because a stiffer star deforms less before breaking. When a neutron star is tidally shredded by a black hole companion, heavy elements spill out and form a kilonova, a glow rich with the fingerprints of freshly minted gold and platinum. For a falling person, the mental picture helps. You don't feel gravity as a force in free fall. You feel the stretching and squeezing that tides bring. Your body tries to follow many nearby geodesics at once, and the mismatch shows up as stress. At first, it's slight. A tug on your shoes, a tightening belt. Closer in, it becomes overpowering. There's no way to brace against it, no trick of stance. The geometry writes the ending without malice or haste. Some quantum gravity ideas suggest that the very final approach to the centre could be softened or changed by new physics, replacing the classical singular point with a region of extreme but finite density. No current observation tests this directly. We can take comfort in knowing the rules. Tides are not random. They scale with mass and distance in ways we can calculate and see. They shape galaxies, raise ocean bulges, drive heat in the interiors of moons, and in the strongest fields they make threads of stars and light. The taffy puller is a home version of a grand, precise effect. In the quiet hours, that neat symmetry between kitchen and cosmos is enough to make the dark feel close and friendly and known. You stand by a clothesline at dusk, pegs clicking in a faint breeze, yet one end tugs harder than it should. There's no hand on it. Still, the line draws tight, pulling your sleeve sideways. That small, stubborn pull is where the hunt begins. In the sky, some stars lean against an unseen partner. They wobble, brighten, and sometimes flare in brief, sharp bursts. The partner stays dark. We follow the tug. We don't look for the black hole itself. We watch what it does to things we can see, the way a hidden dancer moves a curtain without showing their feet. The first sign often arrives as a hard, bright whisper. X-rays. Gas drawn from a companion star spirals inward and speeds up, rubbing against itself, heating until it shines in high-energy light. That whirl of hot gas is an accretion disk, a messy, luminous plate around the black hole, where friction turns falling into heat. The X-rays reach us as flickers, with patterns that tell us how quickly the inner edge turns, how close that edge dares to orbit. In that light, we listen for a hum. Some systems show quasi-periodic oscillations, a heartbeat tied to the tight inner lanes of spacetime. The pitch hints at mass and spin. To find the culprit's heft, we watch the visible star. Its spectrum, thin lines like barcodes, slides back and forth as the star yo-yos around the centre of mass. This shift is the Doppler effect. From the timing and speed of the wiggle, we get the mass function, a flaw on the dark partner's weight. If that minimum overruns the maximum known mass of a neutron star, we have a strong candidate. A black hole leaves no surface to flash. It offers gravity and heat alone. Sometimes the donor star's shape betrays more. As matter spills over through an invisible funnel, the Roche lobe, the star may stretch into an egg, broadside brightening as it turns. Those shape changes carry distance and angle and inclination. Not all of these systems are steady. Some slumber for years. Then, like a blocked sink suddenly freed, they flood. In a transient, a small black hole in a binary wakes and feeds fast. The disk flips from cool to hot, and X-rays spike. Telescopes keep watch, from all sky monitors to nimble satellites, catching these outbursts when they blink on. Afterward, when the light fades, astronomers use the lull to take the star's spectrum in detail. The quiet spells offer the crispest wiggle. There's another kind of hunt, quieter still, where the dark object doesn't need a companion. It can lean on the light of a distant background star and bend it, working as a lens. This is microlensing. A field of ordinary stars in the bulge of our galaxy can, now and then, host a sudden brightening of one star as a compact, massive thing passes in front. The shape of that brightening its slow, smooth rise and fall gives away the mass. If there's no detectable light from the lensing object, that mass might belong to a black hole drifting alone. Some surveys, wide, patient and exquisitely precise, have found events that fit. Follow-up astrometry, the minute wiggle of the background star's position, can clinch the case by measuring the lens's tug on positions, not just brightness. Instruments like Gaia have turned this from hope into measurement. Closer to home, in tight pairs, the choreography can be complex. We infer spin from the glow of iron in the disk at high energies. The iron line gets smeared and skewed by gravity and motion. Red wings stretched by gravity, blue edges boosted by speed, so the asymmetric profile becomes a map of space-time near the hole. There's a more direct speedometer too. The inner disk can graze the innermost stable circular orbit, a natural boundary where stable paths end. If the disk stretches inside that edge, it plummets. If it sticks just outside, it shines. Knowing where that edge sits depends on spin, and spin keeps time in the last swift rounds of light. We also listen with different ears. Gravitational waves, ripples in space-time, have already revealed many heavy black holes far from stars. For stellar mass holes with partners, the gravitational music is often too faint, but a merger's final song can sing across the cosmos. When a transient lights up and a chirp arrives, we get both line and melody, mass and motion together. We are careful with false notes. Some X-ray binaries host neutron stars, which can also flare, burst and tug. But a neutron star has a surface. It bursts in thermonuclear flashes and can pulse if magnetic fields funnel hotspots. The absence of these signatures strengthens a black hole case. So does a mass estimate above about 3 solar masses, the upper limit for neutron stars by our best understanding. Yet nature has its surprises. We hold the claim lightly until the pieces line up. Out in other galaxies, the same game plays on larger stages. Ultraluminous X-ray sources could be stellar mass black holes pushing hard at their limits, or intermediate mass holes feasting more gently. Thin disks, thick disks, winds that scatter and hide. Each piece can make a line look brighter or dimmer. Polished models matter less than steady, careful notes gathered over longer arcs of time. The sky rewards patience. We could wish for a visible face. Instead we get signs on a clothesline. A star's regular tug, a sudden spike of X-rays, a subtle lensing sway, a broad iron smear, a whisper of gravity's ring. Each clue is modest. Together they outline the shadow. The unseen partner is there, not because we see it, but because everything around it can't help but answer its pull. Quietly, across the dark, the evidence holds. The missing hand on the line is the thing itself. Picture a town square at dawn. Pigeons wheel above the cobbles, turning as one around the clock tower. The whole city seems to breathe from that centre. Galaxies have that feeling. Their stars, gas and dust plume and mingle, yet their hearts beat around a heavy anchor. There, in the inner precinct, sits a supermassive black hole, a mass millions to billions of suns worth, compacted into a region smaller than the orbit of Mercury. We don't see a mouth in space, we read the crowd. In our own city of stars, the Milky Way, astronomers watched a cluster of young hot stars, the S-stars, orbit something we cannot see. Their paths carve clean ellipses neat as chalk, swinging to points of intense speed near the focus. The star called S2 streaks around at thousands of kilometers per second, its pericenter crossing inside the size of our planetary backyard. By tracking those orbits for years, the mass of the central object falls out with little fuss. About 4 million suns. That's Sagittarius A star, a quiet giant compared with its quasar cousins, but still the unbudgeable core of our galaxy. The centre is thick with dust and gas, yet infrared light threads through, letting us watch the dance. Other cities show different signs. In some, water molecules spin around the hole emitting microwave signals, mazes bright and coherent. These act like glowing beads on a string, mapping the rotation in exquisite detail. From that spinning, we learn mass and distance with grace. In still more, gas near the core blurs into a broad smear in spectra. The great widths of these lines, blended by high speeds, hint at a deep gravitational well. Tie those widths to the size of the emitting region, measured by reverberation mapping, the lag between a flicker from the centre and the gas's echo, and the mass reveals itself. There is a striking pattern. The mass of the central black hole scales with the velocity spread of stars in the galaxy's bulge. This is the M-sigma relation, a strong thread tying the small dark heart to the vast light body around it. It suggests a long conversation between the centre and the outskirts. As the hole feeds, it can throw light and wind back into the galaxy, nudging star formation, shaping gas. And the galaxy's growth in turn brings more fuel inward. The city and the clock tower grow in step. Some supermassive holes blaze. Quasars bright as 1 trillion suns mark the times when gas rains in and disks glow hard and hot. Jets lance out, narrow and fast, stitching radio lobes across intergalactic space. We see these at great distances, so we know that giants were already in place when the universe was young. That raises a gentle puzzle. How did they grow so big so fast? Seeds may come from heavy first stars collapsing, or from direct collapse of primordial gas clouds with little fragmenting. Accretion and mergers then carry them upward. We don't know the exact mixture yet. As more high redshift quasars turn up, the recipe becomes clearer. We also ask what spins these giants. Spin is the angular momentum, the stored swirl, and it shapes how close a disk can orbit, how jets launch, how light is bent. We infer spin from the shape of X-ray reflections, from the pattern of polarization around the black hole, and from the size of the shadow in high-resolution images. High spin suggests steady feeding from a single direction, or many small sips aligning over time. Low spin hints at chaotic, jumbled meals. Cities can be orderly or messy, their centres remember. Supermassive black holes are not only sinks, they can act as engines. As gas spirals in, magnetic fields twist and funnel energy out. That energy heats and shoves gas on galactic scales. In clusters of galaxies, we see vast cavities in hot X-ray gas, carved by jets from central black holes. In some galaxies, winds blow out metals and dust, thinning the fuel for new stars. In others, trickling flows feed quietly and the hole naps. The square isn't always loud. Sometimes it is only a steady presence as pigeons idle and turn. Our closest supermassive neighbour speaks softly. Sagittarius A star flares in radio and infrared, brief flickers from hungry knots in its sparse diet. Its quietness makes it a gentle place to test gravity, following stars in close passage and watching their light stretch and slow. In the brighter, brasher centres of other galaxies, we use broader tools and accept that dust, weather and crowding blur the view. Even so, the pattern holds. The heart is heavy. The city flows around it. Stand again in the square. Imagine leaning on the rail as the morning stirs. You feel the whole place hung on something deep and steady. The pigeons take their cue from one point. So with galaxies. The giants in their cores don't appear on a grand pedestal. They show themselves in how everything else moves, warms, and sometimes blazes. Quiet or loud, they are the still point in a turning sky. Spread a patchwork quilt on the floor. The squares come from different homes, some bright with small stitches, some faded, some thick. When you sew them together just so, a larger pattern appears, one that no single square could hold. That's how Earth turned into a lens wide as itself to glimpse a black hole's outline. No single telescope could resolve the shadow, but by linking dishes across the world into one instrument, the Event Horizon telescope caught the ring of light around the dark. The trick is interferometry. Instead of a single huge mirror, we take many radio telescopes and let Earth's size set the scale. Each dish listens to the same source at the same time, and we record the light waves with exquisite precision. Atomic clocks keep faith. Later, we bring the recordings together and let the wave crests and troughs interfere. The differences tied to the distances between each pair of telescopes, called baselines, encode the image. Very long baseline interferometry, or VLBI, turns the planet into a stitched mirror. But the mirror isn't solid, it has gaps. Weather, geography, and scheduling leave holes in the quilt. To fill them, we rely on the Earth's rotation to sweep baselines through different angles, and on careful calibration to keep phases in line. Some measurements, like closure phase, are robust against uncertainties. They carry the shape even when the absolute brightness wobbles. Still, when the data is sparse, there's room for different images to match the same samples, so we test many ways to fill the gaps. Independent imaging teams run blind reconstructions, with algorithms that prefer simple, smooth rings, or are willing to admit knots and asymmetries. We check that the essentials agree. The targets are giants with event horizons large enough to see at radio wavelengths across intergalactic distances. The first image revealed a ring around the black hole in the galaxy M87, 55 million light-years away. The ring was thicker than a pencil stroke, brighter on one side, not a perfect circle. That unevenness was expected. The bright arc is a relativistic beaming effect. Gas on the near side moves toward us and its light is boosted. The ring's size reflects the mass and the bending of light around the hole. You don't see the hole itself. If you see a shadow, the region where light falls in after taking one last turn. Later, the same project turned to the centre of our Milky Way, Sagittarius a star. That image was trickier. The gas there changes quickly, blurring over the course of a night. We had to treat not a single photo, but an average of a restless scene. Still, the ring appeared, consistent with the mass measured by the orbits of the S-stars. Two very different weighing scales, one using stellar motion, one using light bent by gravity, agreed. Polarization adds colour to the quilt. Radio waves carry information about magnetic fields where they were born. By mapping polarization around the ring, we see how fields thread the gas, and perhaps how they help launch jets. In M87, the polarized image hints at organized fields near the event horizon, consistent with jets being powered by a magnetic tap into the hole's spin. The shadows aren't silent, they speak through structure. There's restraint in how we read these images. They are not photographs in the way a phone camera captures a face. They are reconstructions from wave samples. We guard against seeing what we expect. We test with synthetic data. We draw from models of black hole accretion, make fake observations through the same web of baselines and noise, then see if the reconstruction recovers the original. Agreement builds trust. Differences point to blind spots in the imaging or in our ideas. The ring size acts as a standard. With mass and distance tied, we can check how gravity bends light in the strongest regime accessible. So far, general relativity holds. No obvious hair, no odd shapes beyond what spin and inclination imply. Yet within the ring, we hope to tune sharper, to see finer features where different gravity theories might part ways. As new stations join and shorter wavelengths come online, the quilt gets a tighter weave. You can feel the human side in the way the data were ferried by hand on hard drives, because the streams were too thick for cables, or in the way a storm over one ocean can erase a line of stitching for a day. And still, when the pieces meet, a pattern emerges, a dark patch framed by light that circles, bends and brightens. The quilt shows not the monster itself, but its working edge. In that simple ring is a presence so strong that it shapes how light moves. The shadow is an absence made visible by everything around it. Hold 2 stones above a quiet pond. Drop them, one after the other, and watch the ripples run together. At first, 2 expanding circles cross and make a pattern of peaks and troughs. Then the rings thin and fade into the wider surface. Space can ripple as well. When black holes spiral toward each other and merge, they send out waves that stretch and squeeze distance itself. We catch those ripples with mirrors and lasers, not with eyes at the water's edge, but the idea is the same: disturbance, pattern, calm. The detectors are long-armed interferometers. A laser beam is split and sent down 2 perpendicular tunnels, each ending in a mirror. The light bounces back and recombines where it started. If a gravitational wave passes, it briefly changes the lengths of the arms differently, making the recombined light brighten or dim. The change is tiny, a fraction of the width of a proton over kilometers of path. Yet with careful isolation, vacuum and optics, instruments like LIGO, Virgo, and Kagra can feel that breath on the pond. The sound we hear is a chirp. Two black holes far apart orbit quietly. The frequency is low, the amplitude small. As they draw closer, they lose energy to gravitational radiation, orbit faster, and the pitch rises. The amplitude grows until, in a brief, furious moment, the horizons meet, and a single, ringing black hole forms. Then the signal damps into silence as the new hole settles. This pattern, slow spiral, swift merge, clean ring down, carries the masses and spins of the pair. A combination called the chirp mass sets the rate of pitch increase. The final ring carries the new hole's properties. By matching the observed signal to banks of predicted waveforms, we infer who crashed into whom. Many events show heavy black holes, 20 to 50 times the mass of the Sun, heavier than most found in X-ray binaries. Some spins seem aligned, others not, suggesting different life paths. Some pairs born together in isolation, others made later in crowded clusters where chance encounters bind strangers. A few events hint at eccentric orbits or higher harmonics, subtle chords in the song that speak of unusual beginnings. Distance is folded into the loudness. Gravitational waves aren't dimmed by dust. They fade purely with expansion and geometry. So, from the amplitude, we estimate how far the source is. If a light counterpart is found, a flash from a neutron star merger, a flare in an active galaxy, then we can tie the distance to a redshift and pluck a value for the Hubble parameter, the measure of cosmic expansion. These standard sirens offer a clean cosmological ruler. With black hole mergers alone, the light is generally absent, but there's hope in statistical associations with galaxy catalogues. The pond is wide, we're learning how to read its surface. Localization is a cooperative game. One detector hears a chirp, but the arrival time alone draws a ring on the sky. With two, rings intersect. With three or more, timing and amplitude put a patch on the map. That patch guides telescopes to sweep for light signals when the merger involves neutron stars, where colonovae bloom. For black hole mergers, we mostly listen and learn about populations. How many, how massive, how fast they spin, how often they meet. After the merger, the remnant black hole can recoil, a kick born from asymmetries in the radiated waves. Some may be shot from their galactic cores if the kick is strong, others shimmy in the centre. These kicks and the spin tilts that seed them carry clues to the pairing pathways. The pond remembers the stone's shape and angle in the way the ripples fade. There are limits we note gently. The low-frequency murmur of supermassive black hole pairs, the ones at galactic hearts, is beyond ground-based ears. For those, pulsar timing arrays have begun to hear a background hum across the sky, a slow wash that comes from many such pairs. A future space-based interferometer, with arms millions of kilometers long, will open that band. The water is larger than one pond. We adjust our craft for different stretches. For now, each chirp is both a report and a reassurance. Gravity works as we expect even when two deep wells become one. The waves carry no air, no surface. They are Spacetime's own trembling. When they pass, nothing is left in the detector but the memory of the pattern, stored in numbers and plots. The pond returns to calm, yet we stand with the thrill of having felt the universe move, just a little, beneath our feet. Set two clocks on a kitchen table, one you keep where it is, the other you lower carefully down a deep well and leave. Later you raise it back and compare. They disagree, not because one ran badly, but because they lived in different depths. Gravity slows time for clocks near heavy masses. It's like standing on a hillside versus down in the valley. The air is thicker below, and your voice moves differently, though your throat works the same. The closer to the valley floor, the slower the ticks. This is gravitational time dilation. In the language of physics, time runs at different rates depending on the gravitational potential. Light climbing out of a gravitational well loses energy and shifts to redder colours. That's gravitational redshift. The two are linked. When you watch a clock near a black hole from far away, you see it slow and its light stretch. As it approaches the event horizon, its signals take longer to reach you, and their intervals gap out. In the limit, at the horizon, the clock seems to halt. From your perch, the fall freezes, but for the clock itself and for the person holding it, time flows as usual. Proper time, the time you feel along your path, remains smooth. Passing the horizon involves no local bump, if the black hole is big enough that tides are gentle at that radius. The paradox of freezing at the edge is resolved by who is doing the looking. Observers at infinity can never see the crossing. The signals they receive arrive more slowly and fainter. The traveller goes on, unaware of any border. This divide shows up in practical places. GPS satellites carry atomic clocks that tick faster up there than ours do on the ground, because they sit higher in Earth's gravitational field, and they move quickly in orbit, which also affects time. Engineers correct for both. Without those corrections, navigation would drift by kilometres. Clocks, finely made and compared, confirm the slowing and the compounding of motion and gravity. Near a black hole, the effect sharpens. If a star circles close to Sagittarius A star, its light, when closest, arrives redder and delayed, a clean measure of relativity. That redshift has been measured in the S-star's pericenter passages. The slower ticking is not a vague idea, but a tangible shift in lines on spectra, swung by gravity's hand. And as we imagine signals sent by a probe skimming the innermost stable orbit, the fast time down there and our slow view up here would paint a story of great patience on our end and swift work on theirs. The pull of the hole also bends paths through time and space. Light can loop near the hole, taking longer routes, a kind of Shapiro delay, so not only do clocks slow, signals must navigate a curved track. When the track curves too much, no outward path remains, the horizon forms, and time for the outer world and time for the inner diverge in a fundamental way. It's easy to give this a dramatic hue, yet it's just the geometry that mass brings. Time is part of the fabric, not a separate stagehand. Gravity is geometry. The presence of mass tells space-time how to curve, and the curve tells clocks how to tick. In a uniform field over small heights, we can treat the effect as linear and mild. Near compact masses, the stack steepens into the hillside's cliff. Some questions remain delicate. What exactly happens to quantum states crossing that boundary? How does the experience of an infeller reconcile with a complete story, told from far away, where the outside seems to encode everything on a stretched horizon? These are quantum gravity matters, and they carry open ends. For our purposes, we can hold two truths. Local time stays kind to the traveller. Distant time stretches their story into a slow, fading whisper. If you step back to the kitchen table, the two clocks look ordinary again. One shows a slightly count different. You reset and go on. The marvel is that nature keeps so strict an account. Every tick depends on the path through the valley or over the hill. Near a black hole, the valley is deeper than anywhere else. Time there takes its time, and somehow that simple, sober fact makes the world feel wider, as if time itself were a landscape we can learn to read. Imagine posting a handwritten letter, then learning that the postbox burns all mail and sends out only ash. You'd worry about what was lost. In physics, the letter is information, the detailed pattern of particles and fields that describe a system. A black hole seems to be that burning postbox. Throw in a book, a planet, a cloud, and from the outside you're left with only mass, spin and charge, the three hairs nature allows. This is the information puzzle. Where do all the other details go? Black holes radiate very faintly through a quantum effect at the horizon. Hawking radiation looks thermal, like heat, devoid of detail. If a black hole evaporates completely, its outgoing light would carry only temperature, not the particularities of what fell in. In quantum theory, though, information should be preserved in time. Evolution is unitary, a word that just means reversibility in principle. A pure state should not become a mixed, forgetful state. Something feels off. One way the field has responded is to suppose that the information isn't lost, but is encoded in fine-grained correlations within the Hawking radiation. Early on, the radiation is thermal to an excellent approximation. Later, as more comes out, subtle patterns build up. If you could collect all the light and read between the lines, you would recover the story. This is expressed in the Page curve. Entropy of the radiation rises at first, then falls, returning to zero when the black hole is gone. Calculations in certain toy universes, where gravity plays in a box or where strings and extra dimensions give us handles, show that such behaviour can come from quantum gravity effects that become important earlier than one might have thought. These islands, regions inside the horizon that contribute to the entropy of the radiation, are a technical way of saying that the book and its ash aren't so separate after all. Another approach reframes the black hole as a hologram. In holography, the physics in a bulk volume maps to data on a boundary with one fewer dimension. The ADS/CFT correspondence is a precise example. A gravity theory in a curved space is equivalent to a quantum field theory on its edge without gravity. In that setting, black hole evaporation is unitary because the boundary theory is. The bulk's loss becomes the edge's bookkeeping. While our universe isn't exactly that curved box, the lesson travels. Perhaps the horizon acts like a screen, storing and re-emitting information in a scrambled way. Scrambling is mixing so thorough that the details are still there but spread wide, like a message shouted in a storm of voices, recoverable with the right filters. There are more radical suggestions. Firewalls at the horizon would break the smooth fall of an infalling observer, resolving a conflict between entanglement patterns we expect. But that sharp break is at odds with the calm crossing predicted by general relativity. Others suggest remnants, tiny leftovers that keep the information forever, though carrying infinite detail in a finite thing feels uneasy. Some tie the answer to quantum error correction, where codes hide data against loss, and the bulk boundary map acts as such a code. The language gets technical fast and arguments run hot in seminars. We can say gently that no one solution carries unanimous weight. Observationally, we cannot watch a black hole evaporate fully. For astrophysical holes, the process is slower than any practical patience. We test the principles in indirect ways, in analog systems where horizons are mimicked in labs, in thought experiments sharpened into mathematics, and in consistent stories that respect both gravity and quantum mechanics. Each step keeps something firm, that physics should be lawful, that information should not simply vanish, and that observers who fall should not burn at the border of nothing. The puzzle invites a kind of humility. Near a horizon, simple pictures break. We hold two frames, the outside view, where light slows and spreads, and the inside view, where all is smooth until the crush. Making them fit with quantum threads woven in is the work. Perhaps the postbox doesn't burn the mail after all. Perhaps it writes the contents on its skin in invisible ink, and the ash drifting out carries hints that, put together, bring the letter back. Not in any ordinary sense, and not in a way a casual eye would spot, but in the deep accounting the world seems to keep. Steam curls off a mug on a cold morning, barely visible and gone in a breath. It's a delicate kind of warmth, easy to miss unless you lean close. Black holes give off something like that, a faint heat that comes not from a surface, but from the way quantum fields behave near the horizon. This is Hawking radiation. It's not steam in any honest sense, but it hints that even the darkest objects glow. The picture many learn first is of pairs of particles popping out of the vacuum near the horizon. One falls in, the other escapes, and the black hole loses a tiny bit of mass. That story captures the idea that the horizon does something special to the vacuum, but it's a sketch. The deeper view is about how we define particles in curved spacetime. Different observers, following different paths, disagree on what counts as empty. The stretch near a horizon mixes up modes of the field, turning what one observer treats as vacuum into what another calls a bath of particles. There's an echo of this in the Unruh effect. An observer accelerating in flat space sees a warm glow where an inertial observer sees none. Temperature depends on the path. At a black hole's horizon, the gravitational field sets a temperature that faraway observers ascribe to the hole. Colder for heavier holes, warmer for smaller ones. The Hawking temperature is thus inversely related to mass. A black hole with the mass of the Sun is colder than the microwave background. Only tiny holes would be warm, and those are rare to non-existent in our present universe. This faint glow ties into a broader set of ideas called black hole thermodynamics. Jacob Bekenstein argued that a black hole should have an entropy proportional to the area of its event horizon, not its volume. Entropy counts the number of microscopic ways a system can look the same on the outside, a measure of ignorance with structure. Hawking's calculation fixed the constant of proportionality. The area law, unusual as it is, suggests that the fundamental information content of a region might live on its boundary, not in the bulk. That's a hint at holography, and at how gravity might encode data. Hawking radiation carries energy away. For an isolated black hole, mass trickles off over extremely long stretches. As it loses mass, the hole warms, and the process quickens. The final moments, if we believe the simplest models, would be a sharp burst of high-energy particles. For stellar mass or supermassive black holes, this is so far in the future that everything else that can happen likely will happen first. For tiny primordial holes, if any were born in the early universe, such end-stage fireworks might be going on already. Searches for their gamma-ray flashes press down on how many such remnants could be left. The physics is careful with frames. For an observer falling freely through the horizon of a large black hole, nothing unusual appears at the boundary. No heat, no spark. The glow is a story told from far away, tied to the notion of a horizon as seen in the time of the outside world. That's fine. Temperatures and particles are observer-dependent in quantum field theory. Like steam seen in a shaft of sunlight, they appear when the angle and place are right. There's gentleness in the effect's size. It doesn't scorch, it whispers. That whisper tells us something precise. Gravity and quantum mechanics talk to each other through the structure of fields in curved space. The calculation, first done with pencil and paper, is now backed by derivations that vary in technique yet agree on the result. In labs, analog systems, fluids with horizons for sound, or light in engineered media show Hawking-like emission, lending confidence to the idea that horizons naturally have temperatures. Open questions remain. Does the emission carry correlations that encode what fell in? How does the back reaction, the way the radiation changes the hole's geometry, play out in detail? What happens in the very last stages where quantum gravity cannot be ignored? We take care to separate the solid from the speculative. The temperature and entropy are well-founded. The ultimate fate still invites many hands. Hold the mug again. The curl of warmth is real, even if it leaves only a damp ring on the table. A black hole's glow is subtler still, and yet it steadies a thought. No horizon is truly black when quantum fields are present. Even in deep shadow, there is structure, and a softness that lets light out by a narrow door. A block of ice sits on a quiet shelf, not melting in drips but slowly thinning, a haze rising you can barely see. Now and then a chip cracks off. Left long enough, the shape changes, then the block is gone. Black holes do something like that through Hawking emission. They lose mass oh so slowly their edge is not rough but mathematically tidy. The time frame is deep, beyond any daily clock. Yet thinking through the end helps us understand the whole. If a black hole sits alone, its temperature tied to its mass sets how quickly it radiates. Heavier holes are colder and evaporate more slowly, lighter ones are warmer and fade faster. For a stellar mass hole, the timescale dwarfs the current age of the universe. For supermassive ones, the lifetime is longer still, almost unimaginably so. Their surroundings, meanwhile, are not empty. The cosmic microwave background bathes everything in a low, uniform glow. While that background is warmer than the hole will gain more from the bath than it loses to Hawking radiation. Only when the universe cools further will evaporation dominate. Feeding and evaporation competed for a long while. The pantry is open. Primordial black holes, if they formed from density peaks in the early universe, could be small enough to matter now. Those less massive than a mountain would be in their final stages today, perhaps bursting in flashes of gamma rays. Observations limit their abundance with no strong signs found, yet windows remain. Bigger primordial holes, if any exist, could darken galaxies as dark matter. Searches for their lensing and their dynamical footprints go on. The story of endings intertwines with beginnings. When a black hole shrinks, it doesn't just get lighter, its horizon area decreases. That seems to rub against the area theorem, which says black hole areas don't decrease. The resolution is that Hawking radiation changes the rules by adding quantum effects, letting area fall while entropy, now including the radiations, respects a broader law. The total accounting still balances. Rotation and charge can tweak the path. A spinning black hole can shed its spin faster than its mass, through processes that tap rotational energy. Superradiance, the amplification of waves reflecting off a rotating hole, can drain angular momentum under the right conditions. In most astrophysical contexts, these drains are small compared with the mass, and they don't bring endings within any graspable horizon. The last act is where our knowledge is soft. As the hole shrinks to very small mass, its temperature soars. The radiation spectrum shifts to higher energies and the geometry changes rapidly. In simple models, the black hole disappears entirely, leaving only the outgoing light. Some suggest a leftover remnant stays, a tiny, stable object that stores the remaining information. Others hold that quantum gravity effects will unroll the endpoint in a way we can't yet calculate, perhaps smoothing the divergence into a finite process. For now, the prudent stance is to admit the uncertainty and to use it as a guide to what a complete theory must explain. If a black hole lives in a bright neighbourhood, near stars, gas, or in an active galaxy, the story bends the other way. Accretion can outpace evaporation by an enormous margin. Feeding makes the hole grow, often crossing many orders of D-magnitude in mass over cosmic history. The ice block in that kitchen is under a warm lamp. It swells rather than fades. Evaporation has a wider reach as an idea. It tells us that horizons have thermodynamic lives, with temperatures and entropies that respond to their circumstances. It links gravity to the language of heat and disorder in a way that is not cosmetic but structural. A curve we once thought of as a mere boundary turns out to keep books. When you look again at the ice, you notice the air's dryness, the light's angle, the faint dents in the shelf. The context matters, so with black hole lifetimes, the universe cools, structures form, jets and winds stir the gas, background radiation dims, the balance shifts through eons. Our equations give a clean line, the Skiad's weather. Somewhere within that expanse, the end of any given black hole will be just a quiet change in state. We probably won't watch it. Yet the thought steadies. Even the deepest wells are not forever. They answer to the same long arithmetic that counts all things out and in. Picture a fireplace on a winter night. You open the flue, the draft draws harder, and the whole house seems to breathe differently. A black hole at a galaxy centre can have that effect. When it feeds, the flow changes far beyond the hearth. Gas streams, stars form or falter, and the galaxy's shape and shine respond. Feeding and feedback are not technicalities. They're a conversation between a small, deep thing and a sprawling, bright one. Feeding first. Gas near the centre loses angular momentum through collisions, bars, spirals, or chance nudges from passing structures. As it sinks, it forms an accretion disk. In the inner region, where gravity is fierce, heat and radiation soar. Light pushes back on matter. There's a natural ceiling called the Eddington limit, where radiation pressure balances gravity for a given opacity. If the hole tries to eat faster, the light blows some of the meal away. Yet not all flows are thin and orderly. Some are thick, some are clumpy, some leak out of plane. In these richer settings, the effective limits loosen, and brief super Eddington feasts may occur. From this hot hearth, feedback flows. Radiation heats nearby gas, making it expand and drift away, thinning the fuel for future infall. Winds, driven by light or magnetically, carry mass outward at speeds of hundreds to thousands of kilometers per second. Jets, narrow magnetically focused beams, punch farther, drilling through the galaxy's halo and into intergalactic space. They inflate radio lobes and carve cavities in hot X-ray emitting gas, as seen in galaxy clusters. These bubbles are not empty. They are filled with relativistic plasma, buoyant and persistent, like balloons rising through a thick soup. The effect on the house is complex. In some galaxies, quasar-mode feedback, bright and windy, sweeps out the central gas and quenches star formation in the bulge. The place goes from busy kitchen to quiet hall. In others, radio mode feedback, quieter in light but strong in jets, stirs the hot halo, preventing it from cooling and raining back down. The central engine keeps the atmosphere from condensing, a furnace that prevents frost. This can solve a long-standing puzzle. Why does hot gas in massive halos not cool like we naively expect? The answer is that the flue is open and the draft keeps the balance. Observations thread these ideas. We see broad absorption lines in quasar spectra, signs of fast winds. We map ionized cones lit by the center's light, shaping the gas on kiloparsec scales. In clusters, we trace cavities and the ripples that fan out from rising bubbles, the energy they carry matching what's needed to offset cooling. On smaller scales, masses and molecular lines reveal outflows from circumnuclear disks. The signatures are many, consistent with a hearth that both consumes and breathes. The dialogue runs both ways. Star formation feeds the center through supernovae and stellar winds that stir and transport angular momentum. Mergers bring gas to the core, and bars in disks can drive it further in. The black hole grows, its spin changes depending on whether the meals come aligned or haphazard. Over time, the mass of the hole and the properties of the bulge settle into relations like the M-sigma relation. It's tempting to see causality in every correlation. We take care. Yet a feedback loop is plausible, steady, and supported by multiple lines of evidence. Not all houses have roaring fires. Many galaxies harbour black holes that sip rather than gulp. Their flows are radiatively inefficient. Much of the energy sinks inward with the gas or leaves mechanically in weak, broad winds. These low luminosity nuclei still affect their neighbourhoods, if more gently. They may keep a trickle of heat flowing into the local medium, keeping it from collapsing into new stars prematurely. Flip the image and consider when the hearth overdoes it. Too much feedback too fast can blow out the very gas that might have built a healthy central bulge, leaving a scattered interior. Timing matters. The most effective regulation seems to come in cycles. Feed, heat, pause, cool, feed again. We see hints of these cycles in flickering central light, in fossil outflow shells, and in changing look active nuclei that brighten or dim as if a damper were turned. In the end, the house stands as one system. The flue isn't separate from the fire, and the air in the rooms isn't passive. A black hole is small by galactic standards, but because of what happens at the brink of its gravity, how light and fields respond, it can touch the whole. You don't need to see the flame to feel the draft. A hand near a doorway will do. So with galaxies. A nudge at the core and the walls whisper. Pick up a small hand mirror in a dim room and tilt it until a lamp's glow catches on the edge. The light changes shape, and for a moment you see the lamp and the room differently. Black holes do that to our thinking. They reflect, by their very refusal to be seen, the structure of the world. We hold them up and find that reality has a texture we hadn't felt on ordinary days. Start with the everyday. Gravity is not a pull, but a path. Space and time bend so that free things go straight along curves, and black holes are where those curves enclose whole regions from which no outward track exists. That alone is a strange, clean note. Then add quantum fields that near the boundary stir a faint glow. Thermodynamics, the language of heat and entropy, steps into the script for gravity. The area of a horizon tallies a kind of information. A ring seen by linked radio dishes fits what geometry says should be there. and ripples felt by soundless instruments confirm how mass moves in its own field. We also learn limits. No signal can cross out once it's too deep. From far away, falls slow and colours redden until they fade. Up close, nothing special happens at the border. Both are true. Reality is layered by viewpoint. This makes us careful about absolutes. It teaches a quiet respect for frames and for the ways different measures can each be complete. Where instinct argues, patient observation leans in and points to a broader sense. There is a human side we can trust. The systems we've built, the timing, the linking of dishes, the clocks that speak across distances, show what can be done when we match craft to clear questions. We sideslip hype and let steady evidence lead. Some mysteries, like the fate of information as wholes evaporate, remain unsettled. That's fine. We can say what is known, what is likely, and where doubts sit on the page. Uncertainty is a room with the window open. Air moves through. When you keep company with black holes for a while, a slow shift happens. They stop being monsters and become tools. A shadow's size checks gravity at the strongest edges we can see. A chirp's pace tells us how heavy stars lived and died. A galaxy's quiet core and its wind-scoured outskirts tell us how growth is shared. The details resist drama, they reward close attention. In the mix of heat and geometry, of light bent and time stretched, there is a lesson about how to look. Start with the small, keep the picture honest, and don't mind if some pieces sit unjoined for a bit. There's also grace. The sky carries structures that are, in their bare bones, simple. A black hole's exterior is described by a few numbers, yet its effects create rich, varied scenes. That combination, plain core, intricate rim, feels like other parts of life. You hold the mirror and find that you are part of the room you're trying to see. Our questions shape the light that reaches us. If you'd like more quiet explorations like this, consider subscribing, and if you have a moment, share where you're listening from and the time. Set the mirror down, the lamp is still there and the room is still dim. Yet something has shifted. Knowing that darkness can have a temperature, that silence can carry waves, and that an image can be built from a planet's worth of listening, gives a gentle charge to the air. Black holes do not end the story. They mark places where our current page is thin. That is an invitation, not a warning. The world holds without our naming it, and invites us to keep looking with care. The night puts a clean edge on things. You breathe, and the house settles. Outside, somewhere, a galaxy turns. Whatever questions are left, they can share the table with the steaming mug, the hand mirror, and the quiet sense that the dark is not empty, only deeper than we knew.